Okay. My name is William Harris. I'm an engineer. My degree was in engineering physics. My specialization was in spacecraft systems. I've had many courses in orbital mechanics and spacecraft design. Um, Today, I want to explore this comparison of the predictive power between the globe model and the flat Earth model. What do they predict, and what do we observe in reality? The first point I want to make has to do with one of the most primitive proofs of a globe. It is the experiment from Eratosthenes. Um, Essentially, the globe and the flat Earth both would agree that as you go up in latitude across the Earth, a shadow would increase its angle more and more as you go higher in latitude. The question is not will it increase in angle? The question is what trend does the increase in angle take? How much does it increase in angle over the latitude? The globe would obviously predict that at the pole, it would be a 90-degree angle. It would be an infinite shadow. But in the flat Earth, it could never be a 90-degree angle. It would never be an infinite shadow, obviously. So the question is, which one do we observe in reality? Of course, the globe is correct. We see these infinite shadows all the time near the poles. Next, star movement. A globe and a flat Earth model both agree that in the North Pole and point C, you would see a circular pattern of stars as they move across the sky. But when you get to the equator on a globe model, you would see stars go from east to west in a straight line across the sky. And on the South Pole, you would see them go in a circular motion again, but in the opposite direction of the North Pole. But in a flat Earth model, you predict that on the equator, you would see not straight line of stars going across the sky, but a curve of stars going across the sky on the equator. And at the point D on the South Pole, you would still see a curve of stars going across the sky, but just more straight. So definitely not a circle pattern. So the question is, which one do we observe in reality? Oh, we do observe the globe one in reality. Sounds great. So we talked about star movement. Now we talk about planet movement. So assuming we were on a globe that is orbiting a star, and there are other planets orbiting the star, we would predict that we would see these other planets and observe specific type of motions from them from our point of view. A really identifiable one would be retrograde. We would see this very specific pattern that you see on the GIF on the side of my screen if we were in that situation, that's to say. And what would flat earthers say about planet movement? They would say, I don't know what planets are. We don't know what those things are. We just lights moving across the sky. There's no way to know what they are or predict how they work or have any explanation for them. So which one has better predictive power and which one do we observe in reality? Of course, we do see planets having retrograde motion, exactly how the globe model would predict. Next. Lunar eclipses, it's a crowd favorite. Obviously, the only object that will always project a circular shadow is a sphere. And in a globe model, you would predict that you would have lunar eclipses, and those lunar eclipses would always be circular every single time. The Earth is always at a different orientation for every lunar eclipse, so it would be a circle every time, no matter what the orientation. The penumbra and the umbra would both be circular. So, and we would predict that we could pinpoint exactly when it would be observable and where exactly it would be observable down to the second. That would be predictable if we were in the globe. Now, if we're in flat Earth, what would they say about lunar eclipses? They would say, I don't know what that is. I don't need to explain what that is. There's no way to predict what they are or how they work or why they work. So which one has better predictive power? The globe does. We do predict these orbits down to the second, I'm at. We do predict these eclipses down to the second in reality and where they're observed, obviously, as well. Constellations and the North Star. Both the globe and the flat Earth theory predict you will see the Polaris, the North Star, in the North Pole. But when we go to the South Pole, on a globe, you would see the Southern Cross on point D and point E. But on a flat Earth model, you'd predict you maybe would see the Southern Cross on point D, but you couldn't possibly see it at point E, right? Because it's on the opposite side of the planet. So what would you see in the night sky of point E? Well, they don't have really any explanation of what they would see because it would have been obvious, but there is no explanation for it, what they see there. They can't see the Southern Cross, that's a guarantee. So which one do we observe in reality? Yes, we can see the Southern Cross at point D and point E. Flight times. So this is real flight data observed in real time from flightaware.com. I encourage everyone to go do this and test these data points live. There's thousands of them every day. Chile to New Zealand is a 12-hour flight, goes 7,000 miles. Seattle to London is a 9-hour flight. It goes 6,000 miles. Um, it's not perfectly linear correlation between the time and that miles, but it's still generally reasonable, especially with the currents of air that go in near Chile in the time of year. So this is what you would expect if we were on a globe. If we were on a flat Earth, I can't tell you exactly the travel times they should be because on a globe, they never have a good scale on exact distances for what a flat Earth map would have because the geometry doesn't make any sense. But you can obviously see that Chile to New Zealand would be about 3 times longer than Seattle to London. So is that what we see in real life? Does Chile to New Zealand have a 30-hour flight? The answer is no. The flight was 12 hours, not even close. The Coriolis effect. The globe has a Coriolis effect that dictates hemispheres on the hurricanes in the north hemisphere and hurricanes on the southern hemisphere will rotate in opposite directions because the equator of the globe is spinning and moving much faster, and the wind is moving faster at the equator than it is at the poles. So it would be different from the north hemisphere versus the south hemisphere. For a flat model, you could argue there shouldn't be a Coriolis effect. But assuming there is, for some reason, a Coriolis effect, it would not change between the north hemisphere and the southern hemisphere. It would be consistent for both. It'd be the exact same. Everything would be turning in the same direction for hurricanes. So the question is, which of these two do we observe in reality? Of course, we see the globe Coriolis effect in reality. Now, this is my last evidence-based argument. This is my favorite one. It's for gravity because it is the most observable, consistent topic in all of science ever since the beginning. Is just gravity. So you can observe it every single day, all day, from a micro scale to a macro scale. Micro being you throwing a ball to your friend with projectile motion, or tossing a nuclear bomb from one country to another using projectile motion and gravitational equations. It can also explain the existence of an atmosphere on a ball in a vacuum because an atmosphere, although it is very, very low density, it is still made of atoms, which still have mass, and mass is attracted to mass with gravity. That is the rule. So yes, the atmosphere will cling to the globe because the globe is a very massive object. That is why an atmosphere does not disperse into outer space. So it can predict we would have an atmosphere. We could predict the motion of the Earth around the sun and the motion of the moon around the Earth using gravity. We can predict the tides of our ocean using gravity because the tides of our ocean is a product of the gravitational pull of the moon on the liquid on the ocean of our planet. We can predict the Earth and all other planets' motion in our solar system, as well as all the asteroids and comets that we see orbiting our star. We can predict the motion of the stars that orbit the galaxy and the motion of all the galaxies in our universe by using gravitational equations. It is the most validated concept in all of science, and to deny its existence is for a fish to deny the existence of water. So what is the predictability of the flat Earth when it comes to something like this? Nada. They don't have anything to predict these level of phenomena. So I've finished with my evidence-based arguments, and now I want to talk a little bit, change it up, and talk about psychology. I want to talk about the psychology of flat Earth, and talk about why in the world does this theory still stick around? It cannot be because of evidence. It is not because of evidence. Because every single opportunity that it could have to prove itself true, it fails and proves the globe is true every possible time. So why could it still exist? If it's not for the evidence, then why? It is because it's about the passion behind the idea. Because the followers of Flat Earth are extremely passionate people. The followers, I want to characterize and profile the followers versus the leaders of Flat Earth and contrast them. The followers of Flat Earth are extremely passionate people. They're insatiably curious. They always want to know why and the next step and the next step, why, and that's awesome. They can also have a distrust of scientific institutions, and they can potentially have predispositions to believe in conspiracy and maybe have a little bit of paranoia as well. Now, let's contrast that to characteristics of Flat Earth leaders. Flat Earth leaders are extremely charismatic and very articulate, as my friend Whitsitt is. A very charismatic and articulate man. But they are also extremely arrogant, They believe they know everything. They're intolerant of criticism, as that would project weakness to their followers. And they're exploitive of their followers. They will ask their followers to support them in their endeavors. And then we need to ask why? What is the incentive these leaders have to push misinformation that they know is false? Because these people are smart. So they know they're not pushing a good faith argument. But why would they want to do that? What incentive do they have? Well, number one incentive is pure fellowship. Having people be loyal to you and follow what you say is attractive. Having attention is attractive, even if you're not following them. I'm giving him attention right now. And that's another incentive they can have. A sense of superiority over their followers. When someone listens to you, that's always nice. And of course, they can make some money along the way as well. So if you have listened to nothing I've said tonight, if you have listened to nothing, just listen to this last part. This is the part that I want to make crucially aware of. This is the most important bit. No individual understands all of science. None, despite what Whitsitt will tell you. No individual understands it all. A astrophysicist doesn't understand everything about quantum mechanics, and a quantum mechanist doesn't know everything about astrophysics. So when you are faced with an unintuitive or unexpected fact, do not throw the baby out with the bathwater. Do not throw the universe out with a misunderstanding. Push Occam's razor to the forefront of your mind and understand it's far more reasonable that you don't have all the information rather than the model for the entire universe is wrong. And that all scientists, almost every scientist, are liars or ignorant. And my last statement is flat earth leaders do not have some special power of understanding things better than everyone else. And please do not fall prey to their con. Thank you. That's my time.